Okay, this next section is about the structure of atoms. And the first part of this section is electromagnetic radiation. The goals are to mathematically relate the wavelength, which is represented by this symbol, lambda, and frequency, which is represented by this symbol, mu, uh, of electromagnetic radiation and the speed of light, represented by this symbol, c. Recognize the relative wavelength or frequency of the various types of electromagnetic radiation. So let's go ahead and take a look here. Doing a little playing here real quick. Okay. So let's take a look at electromagnetic radiation. You should know the different types of electromagnetic radiation, starting with gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. Now, there is one thing I forgot to put in here, and that's this, VIS. That stands for visible. It goes between ultraviolet and infrared. Now, when you see a word like this and an arrow like this, the arrow always points to what is greater. So gamma rays are greater in energy than radio waves. And here below, you see the arrow pointing in the opposite direction. So you can see that as far as wavelengths go, radio waves have longer wavelength than gamma rays, which have shorter wavelength. So, characteristics of radiation. We treat radiation like it's a wave. There's an electrical component and a magnetic component. And an interesting thing about this is that spinning magnets create electricity, and electricity can be used to make magnets. So this is kind of how we make electricity pretty much in the majority of the world. We spin a magnet, and that magnet is attached to something called a turbine. And so you spin this turbine, and you create electricity when you spin the magnets inside of a magnetic field. Well, actually, what we do is we spin a wire inside of magnets and create electricity. At any rate, the key to creating electricity in the world has been, how do you spin that wheel? So one very popular way to do it is to take a large body of water, dam it up, and make it go down. And when it goes down, it goes through these turbines and it spins the propellers, which creates electricity. So that would be like Hoover Dam. Another way to do it is to boil water. And when the water boils, you create steam, which rises. And when it rises, it goes through turbines and spins it. So that's how coal burning plants produce electricity. You burn coal, you boil water, and the steam makes the wheel spin. Nuclear power plants work the same way. The nuclear energy boils the water water turns into steam, and it goes through turbines, and you create electricity that way. So the whole idea behind trying to get energy for the world has been to spin that wheel. And we've been spinning our wheels for quite a while, and it's going to take something innovative for us to stop spinning our wheels. And one of those innovations might be solar energy, because there is no spinning wheel there. Okay. So let's take a look here at electromagnetic radiation. So here's the wave characteristic. And you got to think about this wave as kind of moving down this line here, moving in one direction. So imagine, if you will, you were in this static position here, and these waves might actually be waves at the beach going past you. Okay, so these are waves going past you. Now, mind you, at the beach, we're also talking about the waves having a little trough here. Okay, so what are the things about the wave that are interesting? One is the amplitude, and the amplitude doesn't play a big role for chemistry unless you talk about intensity. The larger the amplitude, the more intense the wave. Lambda is the wavelength, and that's the distance between like portions of the wave. So here we go peak to peak, or we could go from trough to trough, or we could go from here to here. As long as you're going from the same portion of the wave to the next same portion of the wave, that's the wavelength. They'd all be the same distance, as it were. Frequency, which is represented by this symbol here, or often with an F, is the rate at which a peak passes a static position. So that'd be like how many waves per second. And velocity or speed is the speed of the radiation. And for all electromagnetic radiation in a vacuum, the speed is 2.998 times 10 to the 8th meters per second. That's the number you want to memorize. This is often called the speed of light, because certainly light, if we think about it, visible radiation, it does have the speed of electromagnetic radiation. Okay, so you should memorize this formula. This shows you the relationship between the speed of light, the wavelength, and the frequency. So this could also be written this way, which is often the way it's written in a physics class. And I actually kind of like that, where you use the letter F for frequency. So if lambda is in meters, and if mu, or the frequency, is in seconds, you have 1 over second. So C would be meters per second. So here, what we want to do is we want to take a look at a wavelength frequency conversion here. So the frequency of the radiation used in cell phones covers the range from 800 megahertz to 2 gigahertz. Megahertz stands for megahertz, where 1 megahertz is 10 to the 6 per second. And gigahertz stands for gigahertz, where 1 gigahertz is 10 to the 9th per second. What is the wavelength in meters of a cell phone signal operating at 1.12 gigahertz? So here we have the wavelength is what we want. And since this is electromagnetic radiation, we know that the speed is 2.998 times 10 to the 8th meters per second. And we know that the frequency, so here we could do it either way, is 1.12 gigahertz. And we know that 1 gigahertz is 10 to the 9th. So I'm going to write 10 to the 9th per second over 1 gigahertz. So you can see that this translates into 1.12 times 10 to the 9th per second. And we also have the relationship between these three factors. C equals lambda nu. And since we want the wavelength, this becomes that the wavelength is equal to C over nu. And then when we plug in the values, we get 2.998 times 10 to the 8th meters per second divided by 1.12 times 10 to the 9th per second. Now, since this second is in the denominator and this second is in the denominator, they cancel. Okay. And so that means that the only unit that doesn't cancel is this meter, so that will be left. And we basically have 2.998 times 10 to the 8th divided by 1.12 times 10 to the 9th. And roughly speaking, this is my ish. 10 to the 8th divided by 10 to the 9th is 10 to the minus 1. And 2.998 divided by 1.12 will be close to 3, but a little bit less. So I'm going to call this 2.7-ish. So here we have 3 significant figures. Here we have 4 significant figures. So our actual answer, we're allowed 3 significant figures. And let's find out what the answer is. So 2.998 second EE8. And I did not type this incorrectly. I put 2.889. 2.998 second EE8 divided by 1.12 second EE9. And I get back 2.68, 3 significant figures, times 10 to the minus 1 meters, or 0.268 meters. Either value is correct. Now on an exam, this is, what could I give you credit for if you showed me your work here? Well, certainly if you wrote this down on the exam and nothing else, I could give you a point for at least knowing what equation you should be using for this problem. Here, you can see that if we show very nicely how everything kind of gets put into place, that's really nice. Here we got the correct number of significant figures. I can give you partial credit there also. Now here, I would like to see you convert the 1.12 gigahertz to per seconds. Okay, and they give you the conversion factor right there. So this is the kind of work I expect to see on an exam. All right, let's put that off to the side now. And let's take a look at the following question. Electromagnetic radiation. Answer the following based on the figures to the right. So here we have visible light, which goes from 400 nanometers to 650 nanometers. And these letters, VIB, GYOR, stand for the colors that you see for these particular wavelengths. It doesn't give you specific wavelengths, but it kind of gives you an idea. So V stands for violet, I for indigo, B for blue, G for green, Y for yellow, O for orange, and red for, or R for red. So these are the colors you expect to see from low wavelength to, or short wavelength to long wavelength. So answer the following based on the figures to the right. One more figure to the right here is we have high energy X-ray or gamma rays, X-rays, and then low energy would be radio waves. And here I did remember to put biz in there. So let's look at the first question here. Which involve less energy, X-rays or microwaves? So here we have high energy over here and low energy, and you can see that X-rays correlates with high energy, whereas microwaves correlates with low energy. So what has more energy? X-ray energy is greater than microwave energy. So I'm just going to write it that way. Now, which has a higher frequency, radar or red light? Now, if we take a look at the wavelengths here for VIB-GYOR, and actually there is something I want to add to this chart here. Let me think about how I want to say this to you. Well, we haven't really run into the equation that we really need for this part yet, but I'm going to say this, that here, when we take a look at these different types of light, it turns out that the shorter wavelength is actually the higher energy and the longer wavelength is the lower energy. So here, when we take a look here at energy, I'm going to put wavelength here. This is short wavelength, and this is long wavelength. But also, I'm going to put up here, this is also high frequency, and this is low frequency. That's the relationship between those. So once we fill in that, the rest of these answers become really easy to answer. Which has higher frequency, radar or red light? Well, red light is part of visible, and radar is part of radio waves. Okay, so which one has a higher frequency? Clearly visible. So visible frequency is greater than radio or radar frequency. So the tough one about this one is knowing that radar is radio waves. Okay, which has longer wavelength, ultraviolet or IR? So if we take a look here, we can see that the short wavelength is ultraviolet, IR is a longer wavelength. So we would say that IR wavelength is greater than ultraviolet wavelength. All right, now let's take a look at this next one. Traffic signals are often made of LEDs, light emitting diodes. The light from an amber signal or a yellow signal has a wavelength of about 595 nanometers, and green has a wavelength of 500 nanometers. Which has a higher frequency, and then calculate the frequency of amber light. Okay, so when we take a look at the numbers here, we have that amber is 595 nanometers, and green is 500 nanometers. And we're asked which one has higher frequency. So we know that C is equal to lambda nu, and so the frequency is equal to C divided by lambda. So when you take a look at this, you can see that V, or frequency, is proportional to 1 over lambda. So what this means is that if lambda gets to be bigger, the frequency gets smaller. And if lambda is small, the frequency is large. It's called an inverse relationship. So I don't actually need to calculate anything here. I can take a look here and I can say, since the frequency is proportional to 1 over lambda, the shorter lambda gives higher frequency. So 500 nanometers gives a higher frequency. And that would be the green light. All right. So which has the higher frequency? Oh, I'm sorry, down here. Which has the higher frequency? I should move everything up a little bit. The answer is the 500 nanometer. Shorter wavelength, higher frequency. Now calculate the frequency of the amber light. So the frequency of the amber light is going to be C over lambda, which is 2.998 times 10 to the 8th meters per second all over the wavelength, and the wavelength is 500 nanometers. Now here, this should say 500 point nanometers, so I'm going to put point here. And instead of nanometers, I'm going to put times 10 to the minus 9 meters. Now that's an acceptable thing to do, is to replace the nano part of nanometers with 10 to the minus 9, because that's what it represents. Okay, so the meters cancel. You see the second doesn't cancel, so that means my answer is going to be per second. And then here, when I take this 2.998 times 10 to the 8th and divide it by this, I'm going to get a pretty big number, because 10 to the minus 9 is going to become 10 to the plus 9 when I put it in the numerator, and that'll add up to this, and it'll be 10 to the 17. And then I have basically 3 divided by 500. So that'll cut down my 10 to the minus 17 a little bit, and maybe make it 10 to the 15 or something like that. Or maybe 10 to the 14. We'll see. 2.998 second EE8 divided by 500 second EE negative 9. And I get 3 significant figures. I get 6.00 times 10 to the 14 per second. And there's your answer. Okay, so you want to be able to use that equation fairly convincingly and show your work. And that's the end of our first section. Thank you for listening. One of these days, I should just memorize the end meeting button and go from there. But there we go.